All right, so today we're just going to pick up where we left off last time, and continue from there. We've been focused on learning about the command line interface, and sort of getting basic concepts of computing understood. The computing environment, the development environment that we're going to work in as software developers, and which means that we're writing source code, compiling these source code files into executable files and testing them. So that is the lab one, and everybody needs to have this remote Git repository set up. I think most of you have done that already, but for those who haven't finished that process, you need to hurry up and get that done quickly. Please talk to me about that during lab today. Now, for those who have a repository already set up, Jaron Willis, the TA for the class, has already evaluated your submissions for lab one, which was pretty simple. It was 2 files, hello.s and hello.cpp. You needed to have written those into your source code repository. So we used can I use your example again? What's your name? Oh, it's Schmidt. Right. I forgot the first name. Sean. Got it. Let's take a look at Sean's work. And this is what, when Sean cloned his repository, this is what you would have seen, which is this README file with some instructions, and you need to carry out those instructions. So you need to run these 2 commands to configure what's called your Git command line client. And now for Sean what he does is he creates these files, hello.s, hello.cpp, that you need to add them to what's called a staging area, a local staging area. Then you need to commit them into your local repository. Then you need to push those revisions to your remote repository. So it's 3 steps. Let's see, I have those 3 steps right here. You need to be in an appropriate location. You don't have to be exactly in there, but you could be in the 201 folder. That works well too. But then you would need to prefix the file names with the folder that they're in. So you do these add operations. Here, these 2 operations do what's called staging. They take those 2 files, place them into this holding area. And from that holding area, then you commit. And you say everything that's in the staging area, the holding area, we want to make we want that to comprise the next revision of our repository. And so we commit that. Now that change happens locally on your local system. So if I look here, if I do ls -a, that means display all files, you'll see there's a folder in there that's hidden. The name of the folder is .git. So on Unix type systems like OS X that I'm using, that any file that starts with the dot character is considered hidden. So the suggestion to tools that operate on files is that the user shouldn't, by default, see the presence of this subfolder. But we can force the viewing of it with the ls command by using this argument here, -a, this modifier. And so this is where your local repository is stored. And you'll see it's a folder. .git is a folder, and in there you've got subfolders and files and so on. You'll never need to operate on that file directly. It's there as kind of like a control system. But it does contain a snapshot. It contains all previous commits that you issue. And each commit, you can think of a commit as a snapshot. So you actually, as long as you have this repository, you have infinite undo on your project. So at every point that you did a commit, it's like taking a snapshot, and you could actually revert back to any one of those points. So that's how you operate on your what's called your local repository. Now there's a remote repository. I can't access the repository that's in your machine, that's in your home folder, wherever that is. But I can access the repository that I set up for you that you cloned from. That's called your remote repository. So your local changes are transferred to the remote repository through this push command. So git push. Make that larger. So now, when Jaren grades your work, if everything is good, you get a perfect score. And then you'll see the score here. We'll have given you, a 2-digit code, a 2-character code, and so that's your secret that we share with you, and you'll be able to see how many points, what score you got for each of these gradable components in the class. So you can set that. You can also look at the class average as well. But if you get a score that is under a perfect score, then we want you to know what it is that you did wrong. So what we're doing is adding a file to your repository. So we write a file into your remote repository. So you need to actually retrieve that to see the reasons for a score that is not a full score. So you need to learn how to run this command. It's git pull. Now I'll be getting 2 things. I'll be getting Sean's push and I'll be getting Jaren's push, assuming that Jaren pushed something. He may not have. And he didn't, I don't think. Jaren did not push something. So we can assume that Sean got a perfect score. So congratulations, Sean. And but that's it. That's how you work with this remote repository. You can see we have 3 people, working on Sean's repository. So 2 of them, Sean and Jaren, are writing into it, and then all 3 of us are reading from it. So that's how the repository is working. Are any questions about that? Yeah.
Is the README file that's the one that has a 2-digit code?
Huh?
The README file there?
The 2-digit code, the README file is in there. That's right. So I'm not going to show that.
You just press ls readme dot md, right?
ls
readme dot md to find out what the 2-digit code is.
No, you open the README file in your editor. So you can use Nano, with README, or if you're learning VI, you can open the README file with VI. Like that's how you do it from the command line. But if you're in the lab and you're running gedit, for instance, you can open the file in gedit. So it's called a character data file. It's a file that contains pure character data. All source code is stored in files that are pure character data. They're not like in Word documents or spreadsheet files. Word documents and spreadsheet files have special proprietary, markers in there, information in the form of byte sequences or numbers that are not meant to be interpreted as characters. And source code files like hello.s and hello.cpp, those are pure character data. So we can use a generic text editor to view them. The readme.md file is also pure character data. The MD, by the way, is short for Markdown, and Markdown is a simplified markup language. Like HTML is like a markup language, and it's getting a little bit popular with programmers these days. So I just thought we'd use it. And you see Markdown used a lot on a big programmer site called GitHub. And so you see Markdown there used quite a bit. So it's sort of catching on. So I thought we'd have a little bit of exposure to this Markdown syntax, although it's not that important. All right. So I just seeding it into the temp folder. Let's take a look at any other questions, by the way, on the repository or command line. Let's start looking at the labs that we'll be doing this week. So here's lab 2. it's titled expressions. Right? So when you write code or read code, you need to sort of think about expressions. So code is generally a sequence of statements, and the statements are built up from these sub-expressions. It's kind of like writing in English. So you have a sentence that's like a statement, computer language, but the sentence has subcomponents. It has a subject and it has a predicate, right? So that's one way of breaking a sentence into two pieces. And then of course the predicate can be broken down into the main verb, the helper verb, adverbs. You have ways of sort of parsing a sentence, breaking it down into its component parts. And you need to think about that when you're learning a computer language. It's very much like a spoken and written language, a natural language. You can say a natural language is different than a machine language. So this is a lab that gets you sort of warmed up to the language. Let's look at the first exercise. And the first exercise is learning how to use some mathematical expressions. How do we use those in computer code? And let's take a look. We'll just do this together. And before I do that, okay, so let's see what it says. Write a console program that prompts the user for 3 double precision floating point values x, y, and z. So double precision floating point values. Well, double precision means twice the precision of the ordinary precision. Now, ordinary precision for a floating point value is 4 bytes. So double precision is 8 bytes. So you can store a more accurate number and a larger number using double precision than regular precision. And we're talking about floating point values. So that means there's a decimal point in the number. There's a fractional component to the number that's being represented in the computer memory. The opposite of this is integer value. An integer value has no decimal component. It doesn't represent a value that's in between two integer values. So it's an integer number. So integer numbers are simpler. They take less hardware, simpler hardware to work with integer numbers, to add them, to multiply them, are easier than to say add or multiply floating point values. It's more complicated. So floating point values have this thing called an exponent. So you can represent very large values by representing them with these exponents. So it's like say for instance, like in a chemistry class, you might see a number like 9.3 times 10 to the 23rd. Right, so it's a big number. And so a floating point representation of that in the computer would store that in either 4 bytes if you're going single precision or 8 bytes if you're double precision. So normally you would use 8 bytes, double precision. That's the default. Default is double precision. So you see these declarations in code all the time where it says double. Let's see if I have it in here. I'll show you that in a minute. And before I do that, let's start, and I recommend that you use this process, and I'm sure you already do anyway. Let's start, we're going to solve this problem. So we're going to make a directory called, what do I call it, L2. Is that the name I asked you to use? I'm not sure if I did. Maybe it's lab2. Let's do that. Did I specify the name? Oh, lab_2. I'll use the move command to rename that folder. There we go. I'll cd into there. I'm just going to run this screen program. It gives me virtual screens to toggle between. And now let's in the first problem, let's see how I asked you to do this. Create a file with this name in this folder to hold your solution to this problem. So that's the name of the file. I'll use VI. You can use a different editor. I pressed I to go into insert mode. And before we start doing this, well, here we need to have code that illustrates the sum of x, y, and z, the sine of x, and all of these other mathematical calculations. We need to write code that does these. And we also need to include in that code a code that prompts the user for x, y, and z. So we want to prompt the user. That means ask the user to provide 3 numbers that we read into the program. And then we perform these calculations and display the result. Let's do that. Now, before I do that, let's start with a hello program, just to make sure that we got the editor working, we remember how to compile, and that the compiler's set up to go, just to make sure our development environment is ready. And and this is how you would normally work anyway. That's how I would normally work. I will always start with a hello program. I can't imagine anyone who doesn't. So let's see, I'll go back to this assignment, and it's down at the bottom. Here's our hello program. You could also copy that hello program from Lab 1 and use that as a starting point. So this just says hello. Oops, is that main? No, sorry, it's ex1.cpp. Should say hello. It does, good. So that's working. All right, now we need to prompt the user for 3 values. Enter. I'll do it like this. I'll say x equals, and then let the user type something in. After the user types something in, I'll prompt the user for y and z. And I'm going to do it like this. Let's run that. Oh, you just printed everything out all in one line. So what we need to do is, the code is just running through here. When we print out x equals, and then we have a space, we want to wait. So we want to wait until the user types something onto the keyboard and hits enter onto the keyboard. So we can do that like this. We need to declare the variable x. It's a double precision floating point value. There's a double precision floating point value x. That's how you do it. This is called a data type. We're telling the computer, we're telling the compiler, we want memory to store a double precision floating point value. And we want to name that storage area x. So we want 3 values represented in computer memory, x, y, and z, and they all label these 8-byte sequences where we're storing a double precision floating point number. And so now we prompt the user. After we allocate the memory here, then we display something to the user, and then we read it in. Oh, this is not correct. this should be, it should look like that. That's called the input operator. This is the output operator. This is an input operator. These are operators that work on streams. So the left-hand side of the operator, right? Operators have operands. And this is called a binary operator. These two are binary operators. And the first operand is on the left side, and the second operand is on the right side. Binary, it means just two operands. There are operators that have one operand, and there are other operators that have three operands. And we'll look at those later. All right, let's do the same thing for Y and Z. So we print X, and then we wait for the user to type it in on the keyboard. We'll need to compile. We modified the source code, so we need to regenerate the executable. Now let's run it again. There it is. It's asking for Y. That's 2 points X. Enter in a value. Now X asks for Y and Z. It takes 3 values. And these are valid. You know, we're not going to look at handling invalid entries at the terminal window. We're not going to look at that in this class. Right? So we're not going to worry about the user doing that. So it basically crashed. Okay, so we're not going to deal with that. I mean, yeah, in a real program, you would have to deal with that. All right. All right, after we have these values, we're going to calculate these formulas. We're going to calculate these calculations. We're going to make these calculations. The sum of X, Y, and Z. Now let's do it like this.
So count is like an easier way to say like display this information.
Oh, cout? Cout is an identifier that represents the standard output stream. And this is an output operator. It says, take this string, the byte representation of the string, and send it into the standard output stream. By default, when you run a program at the command line, the standard output stream is the display, but we can redirect it to a file. And it could be redirected to other systems as well, I believe. I don't know what they are, but some other things. And for instance, when we run this, see we're outputting values to the screen. But if we run it like this, wait, let me show you. If we run it like this, we say, oh, we don't want this, the standard output stream to be attached to the display. We want it to be attached to a file name of file. Well, and look what happened. It created file, and it wrote its output into the file. So we redirected the standard output stream to a different mechanism, a different recipient of the data. Is that okay? All right. And by the way, this is the opposite. This is a standard input stream. The standard input stream is a keyboard. We can, when we execute the program, we can modify. We can change the standard input stream, and declare that we want the standard input stream to be the contents of a file, and then the file contents will be streamed into the program. And all operating systems have that notion, by the way. So Windows, Mac, Linux, all of those. All right. Here's some modifications. So what we do here, now I'm doing something called cascading this output operator. So the output operator appears twice in this line. And, you know, normally when you see two operators appearing in one statement, that you, a left to right order of execution takes place. So the first operator does its action first, and then the second operator comes in. So, you know, what is the operand? What's the left operand of this operator? What's the right operand? Well, the left side of that operator is cout, and the right side of that operator is that string. This is an expression. It's an expression that is a sub-expression within the statement. And the statement is bigger. I've highlighted the sub-expression, but the statement is actually bigger. So we know what the left-hand side and the right-hand side of this operator is. But what is, and this one here, clearly the right-hand side of this operator is 0. But this operator here, the right-hand side of that operator is the value 0. But what is the left-hand side of that operator? The left-hand side of that operator is whatever, remember, it's left to right execution. So the first operator runs and it evaluates to something, and that becomes the left-hand side of the second operator. This evaluates to cout. So you can just mentally replace what I have highlighted there with cout. You know, it has a side effect of sending some bytes into the output stream, but then, you know, as an expression, it evaluates to the left-hand side. So if we used a different stream here, because cout is just one of any number of different streams that we could output into. If whatever is on the left-hand side of the output operator, that's what the expression evaluates to. So the reason for that is it allows us to cascade these output operations. Now let's test this. So I'm printing this statement, this sentence, and then we're going to print a 0. Let's take a look at that. I'll do that. I'm using the up arrow and down arrow. That's called the command history. So I don't want to have to type in the commands again. So I just use the up arrow. I'm lazy, and I have to do a little work there. So x equals 1, y is 2, z is 3. The sum of x, y, and z is 0. It's not quite clean because the prompt is written right after this, right after our output occurs. So let's clean that up. We can cascade a little more, actually. Let's put a period there and a new line. That's a dot. That's because it looks like a sentence. Let's write a period. And then let's output a new line character. It looks a little better. So we're just solving this thing incrementally, one at a time. We need to output the sum of x, y, and z. What is it going to be? We'll call it the, there's many ways to do this. And one way to do it is like this. We can just put the expression right in there. See, now you're looking at, you know, a big collection of operators here. So when you look at this, you see this plus sign here. This has higher precedence than this output operator. So it means the compiler will generate code that performs that action first. So X, Y, and Z will be added together first before either of those output operators are used. Well, actually, the one on the left here. Right? So this sub-expression evaluates to C out. And that becomes the left-hand side of this operator. And the right-hand side of that operator is the result of this sub-expression. But what does that sub-expression evaluate to? It doesn't evaluate to C out. It evaluates to the result of adding the three numbers together. So we take whatever the user entered in for X, adds it to whatever the user entered in for Y and Z, and that sub-expression then evaluates to that sum. And that becomes the right-hand side of this output operator. Let's see if that works. So 1, 2, and 3. What's the sum? 6, right? Okay. There it is. We got it. Let's do the other ones now. Well, before I do the others, I want to show you an alternative. Maybe this isn't very readable for you. And what we'd like to do is break it into steps. So let's declare a variable called sum xyz, and we'll declare that variable that allocates memory to store a floating point value. And then we take this expression and use it as the right-hand side of an operator, this operator right here. But I'm not going to tell you what the name of that operator is. Can you tell me what the name of that operator is? That's an operator. What is the name of that operator? It's not called equals. It's called assignment. This is the assignment operator. It takes what's on the right-hand side and assigns it into the left-hand side. So you need to start thinking about equal signs as assignment operators. Okay. So we calculate x plus y plus z and assign it into this variable sum x, y, and z. And now we can use that variable sum x, y, and z in place of this more complicated expression. Let's test that. We have the same result. So we're striving to make this more readable. Now there's another thing you could do here. As you can see, there's many ways of solving a problem. Even at this simple level, there's so many different ways of organizing your code. And the reason to think about this is not because the computer will give you a different result if you organize your code differently, although it could if you organize to that degree, but the purpose of reorganizing your code or organizing it thoughtfully is you want the code to be readable. It needs to be understandable, maybe just to you, if you're the only one that's concerned with it, or it has to be understandable to others who are also reading that code. But the computer, being understandable to the computer, that's a compiler issue. That's you and the compiler. You have to, of course, be concerned with that and handle that as well. But readability by other humans, including yourself, is also an issue to be concerned with. Now, I'll just show you here that actually you can organize it like this. You can declare the variable and initialize it all in the same statement. statement ends with a semicolon. Maybe this is more readable. This will give the same result. You know, internally when the compiler generates the code, you're going to get the same machine instructions, going to get the same output. The question is, what's more readable to the human? Here's another example. You could do it like this. Maybe that cascading of output operations is just too confusing. How about if we just break it out into a few lines? See, a statement is not terminated by a new line. A statement is terminated by a semicolon. So that gives us the freedom to break a long statement, spread a long statement out across several lines. You can't do this in all languages. You can't do this in Python, for instance. In Python, one statement, one line. I think. Anybody use Python? But most languages allow you to spread a statement out onto multiple lines. Maybe you don't like it this way. Maybe this is more readable to you. We're going to get the same result. Maybe I want to put a blank line in there just to separate that these are also similar. I'm just going to group those together. And this is kind of a separate thing here, although it's related to this, isn't it? So maybe we want to put a comment in there, something like this. A comment, we can start a single line comment with // It's good to use comments. So you can work on that. Obviously, you can keep working on the comments quite a bit. Maybe add some, take some out, whatnot. But I wouldn't put any comments in here because, I just you can just read the code as well. So you don't want to put in unnecessary comments. The code itself speaks for itself. When the code doesn't speak for itself, a comment is critical and important because if you're learning the language. And you might want to say, mention that this is an input operator, for instance, just because in that context, that extra comment is meaningful and useful to you. But for someone who already knows the language, you wouldn't make an obvious comment like that because it's more to read and it doesn't help the reader understand the code any better. It just makes it harder to read. So that's something called, those would be unnecessary comments. Many times, something in your code is not obvious. It's not directly readable. The code doesn't speak for itself. In those cases, a comment is essential. Okay, let's see, make sure we didn't break anything. Looks okay. Now let's go through and do the rest of these. Actually, but you can do the rest of those. Do you want to see me do any of these?
Yes.
Huh?
Yes.
Which one?
The sign of X.
Sign of X?
I think you spelled C out.
Oh, thank you. I don't think this is going to compile. Does anybody know why I think that? Let's see if it doesn't compile, and then I'll ask a better question. Why didn't it compile? Huh? Oh, sin x is undefined. Sin, S-I-N, is an undeclared identifier. The compiler is saying, I don't know what that is. A sign is defined, is a part of what's called the standard library. Just like IO stream is a part of the standard library. The IO stream defines C out and C in and these operators for those streams. There's another, and the library is, the C++ standard library is very big. It's broken into pieces. So we just want to bring in, one piece at a time as we need it. So there's a piece called CMath. And that is, that designates that part of the library that defines the mathematical functions. Let's make sure I saved that. Let's try that now. That worked. Okay. So now it's going to calculate the sine of x. So let's test it. What is the sine of 0? 0. Let's test that. Sine of x is 0. Okay, let's try the sine of 90 degrees, right? Oh, do you think it uses degrees or radians?
Radians?
Huh? Radians, right? What's 90 degrees in radians? Pi over 2. So we don't know what that is, right? How about, let's try this. How about 3.14159? Huh? That's pi. So what's that going to give us? What's the sine of pi?
0.
It should be close to 0, but it's not exact, right? Because pi is an irrational number. Whoops, I messed it up. Look, the sine of 3.14159 is 2 times 10 to the minus 6. It's close to 0, right? That's the exponent is a big negative number. So it's a tiny value that's close to 0. That's because we didn't get exactly 360 degrees. All right, so we now, at least we've demonstrated that the argument, the units for the sine function is in radians. We know that now. We've tested that. Any of the others you want to look at? You got to do this in lab. So
Log 2, right?
log base 2 of x. Compute the log base 2 of x. I can't remember. Is it that? Or is it just log? I think it's log 2. What? Anybody have a book? Is it so log base 2 is not defined? So we got to do something like that. Is that right? You know, I thought it was log 2. I might be wrong. So log base 2, it's the log base something divided by the log base the same something 2, right? For the math people, did I get that right? Sorry, okay. But I think that's not necessary. I think these answers are wrong. So what's the log of, what's a number we want to take the log of? 1. What's log base 2 of 1? 0, right? Yeah, got it. Okay, so, but what is the log base 2 of 4? 2, right? Okay. That looks good. But what about this? What if we do that? That's what I thought. That's what I thought the answer was. Let's try to run that. Okay, drum roll here. Log base 4, log base 2 of 4 is 2. Ah, it is. First of all, what do we know here? We know that log 2 is defined. Otherwise, the compiler wouldn't compile it, right? If I did this, watch. Suppose I did log 6. Log 6 is not defined. So log 2 is defined, and we know that. And when we use log 2, we get the same answer that we do when we use this formula that we know from our math classes. And so I'm pretty sure that this is, this log 2 is part of the standard library. So we don't need that. Although you could leave it in there for documentation. And I don't know why they didn't say anything here about it, but they didn't. How about this? C++ standard library log 2. Oh. This looks like, I hit the site when I write code in C++, so it looks like log 2 is defined. But it could be compiler dependent, so I don't know if it's part of the C++ language definition. That's what I don't know. And so we'd have to do that research. So to play it safe, if we didn't want to spend the trouble to verify that log 2, if we wanted our code to be absolutely portable, we didn't know who was going to build it, and we didn't want to take the time to find out if it's in the language definition, then we'll just play it safe without them. All right. Are we done with that one? We've got some others to do, right? Cosine, and there's this more complicated thing here. Okay. Oh, I did. I say log 2 right there. Oh, all right. And you need to include CMath up here. And then you need to do these operations. I actually don't have a, let me see. Let me see if I can clone a repository. No, I don't have it. This doesn't exist. Sorry. All right. But these are the commands. So I don't have a test repository set up to show that to you. So I don't want to spend the time doing that. But these are the basic commands to use to get that file in the repository. You can cd into this folder, use this git add command with the file, use git commit, and then git push. I said git commit. I merged the two together now. I've got git commit. And so you can, you don't have to wait till you get to the very end of the lab to commit your work. So this is a good way to back up your work. Also, if you need to leave or work on your files later, you can do that. At least you have something written into the repository. You haven't finished the assignment yet, so you can interact with the repository later on, which you do here. Okay. All right. How about this exercise, unit conversion? Write a console program that converts meters into feet and inches. So we're going to, we'll prompt the user to enter in meters. The user enters in a value, and then we display how many feet and inches that number represents. The program starts by asking the user for a measurement in meters. The program should accept a floating point number. After getting the number, the program computes the number of feet and inches equal to the specified number of meters. The program outputs feet and inches as whole numbers. The program should round the number of inches correctly. Test that your program produces the following outputs for the given input. So this is a test input, and this is what it should output. This value should equal 1 foot. Place your code in this file. Let's get that done. So we're in lab 2. I'm going to copy the existing file to the new one. So that'll be our starting point. Let's read in meters from the user. Declare a variable meters, prompt the user to enter in the number of meters, read it in. Let's see if we got that right. Two meters. Okay, so it reads a number and it doesn't crash. Let's calculate the number of feet and inches. Now we're using floating point numbers. Well, we don't have to actually here. We can do it like this. The feet value will always be in integers. Will be an integer. So if you look at this, we're not displaying a fraction of an inch. We're going to round off to the nearest inch. So I'm declaring the feet, and also feet. Feet will be in whole numbers. We won't have 1.5 feet because that will translate the half part into inches. So we can declare this variable feet as an integer. And well, there's a way to convert meters to feet. How do you convert meters to feet? You divide by this, right? Or something. Not sure what it is. How many feet in Yeah, how many feet in a meter? So that's how many feet in a meter. So 1 meter is this many feet. So I want to know, that's not the number we want, right? We want to go feet in a meter. We want to go the other way. Oh, that's what we want. 3048. They're using 8 there. Is that right?
Just rounded.
They're rounding it? Is this what? That's not the definition of a foot in a meter, is it? Is it? 348. Maybe that's good enough. Let's use that. Sometimes you see this symbol, ENDL, end line, and that has a similar effect to outputting \n, a new line character. But it flushes the out, what's called, it does an operation called flushing the output stream, which is, some sort of extra guarantee that you get with that. All right, let's run that. So meter, whatever, 3 feet. So 1 meter is more than 3 feet. It's 3 feet and 3 inches. Now, this calculation here, I put a 1 in there, right? So 1 divided by this. Now that's going to be a floating point number. But we're taking meters as declared as a floating point variable here. This constant is written as a floating point number. So the compiler interprets this symbol as floating point division. There's 2 kinds of division. There's floating point division and there's integer division. And you have to be always on the lookout to notice which of these 2 forms of division that's being used in your code. Here it's floating point division. So the result of this operation is a floating point value. Well, we try to store it into a storage location that's designated as holding an integer. So the compiler has to generate extra code to do a conversion. The compiler generates machine instructions that convert our floating point result to an integer result. Now, how does it do it? How would you do it if you wrote the compiler? Would you round the number, or would you truncate the number? Do you know what I mean by truncate? You truncate means you chop off and discard the fractional component. So if it was 1.999, truncation means you just have 1. Rounding means you get 2. Okay? So would you truncate or round if you were a compiler writer? Well, let me tell you, compiler writers always truncate. They never round. So when we do this calculation, we do that division, we do the integer division, and then we do this type conversion from a floating point value to an integer value, we lose the fractional part. It gets thrown away. It doesn't get rounded, it gets thrown away. But that fractional part has inches in it. So we want to pull the inches out of there. So how many inches does it have? It has got to take meters. And, I've solved this problem before, so I know the trick. Okay, here's the trick. Well, I shouldn't do it in many ways. I'll show you one way. We're going to take meters, and we're going to convert, oh, no. We'll take meters. This is the meters converted into feet. That's the meters converted into feet. And just if you look at this expression, we haven't stored it. If you just look at that expression and wait, don't assign it to feet to inches yet. This expression evaluates to a floating point value, so it has to. It's not dropping anything. So if we multiply by 12, that converts feet into inches. And then we can store that into inches. But that's the total number of inches, including, the feet component. And this is going to get tough here, but we're at the end of the session, so I'm going to kind of give you the answer. We need to take out that part which represents the feet. Oops, we didn't output it. Oops, need a space in there. Three feet, 3 inches. What about 2 meters? 6 feet, 6 inches. Oh, there's a problem with that. We're not almost done, by the way. I hear you relaxing. Hold 30 seconds. The answer should be 7 inches. We're getting 6 inches. What's the problem? We're truncating. Well, and the instructions say round. The program should round the number. How do you round a number? In any language. Well, there's a round function you can use in many languages. But if you don't have a round function, what do? Just add 0.5. That's it. Add 0.5 before you do the truncation. That's equivalent to rounding. We got it. All right, that's it.